All right, so our next step now is going to be going into section 48, right? 48. I think that's, no, 47? I'm losing track now. So basically we're going to convolutional neural networks, right? So this is basically, we're taking neural networks and we're going to modify them to be basically geared towards image recognition. And I will say real quick is that convolutional neural nets, also abbreviated as CNN, they are not necessarily just for image recognition. They actually can be used for other things as well. But usually in general, we introduce it as, imaging because it makes a lot of sense compared to other kind of ways to apply CNNs. And we'll talk about that in a second. But before we talk about CNN and stuff like that, I think it's a useful thing to see or talk about is like, how do you deal with image recognition in general? So one thing to note is that a computer, if you're not familiar with digital photography, basically computers picture images with pixels, which are basically just values. Basically, it's a number. And in that pixel, right, that number is going to represent basically how bright or how dark it is. Okay. Zero, I have to get this wrong. Believe zero being dark, 255 meaning bright. So zero meaning that there's no brightness, 255 usually in general is the brightest. So the higher the number, the brighter it is. So if you imagine like really quickly, if I kind of draw a little quick picture, I should just find pictures to do this since I don't have to draw so much. That's okay. If you imagine your pixel or your picture right here, I'm gonna draw a really low resolution picture with horrible non-symmetric pixels. But if you imagine like if I drew like something like something that looks like a circle, so I would fill this one in like dark right here, maybe this one like this, and then like this. So there's something that looks like an L. Okay. So what this would look like essentially is a bunch of numbers where if I drew on top of this, so hopefully this stands out pretty well, is that let's say this is like, like 100, and this is 0, 0, 100, 0, 0, 100, 100, 100, 0, 0, 0. Okay, so that's kind of like how pictures are imaged. Now, if it's just one single, like you can imagine a 2D picture, right? With these values, it looks like a matrix, right? And that basically will be grayscale. So a grayscaled image really is just a 2D matrix. So basically it's just saying, is it dark? Is it closer to white or is it closer to black? So if it's black, for example, it'll be a different value versus white being a higher value or something like that. And in between there will look more grayscale. Now, if you want something like colored image, is that essentially what you have are different like channels, they call them. And so, for example, this might be the blue channel with its own set of like little numbers. This is like the blue channel. And then maybe, for example, we have like another channel, which is like the red channel with its own numbers. Okay. And then let's say, for example, it's red, green, blue, which is pretty typical. We have our green channel, and that would be like a third matrix. Okay. So you can think of it as like a 3D tensor, right? So essentially like, we have different layers essentially. And note, depending on the picture, there are technically things you can have 4 channels and stuff like that. Sometimes alpha is built into it as well. But in general, and when we say something's colored picture, it means that there's more than one channel. Okay, so in general, we'll kind of think about grayscale because it's kind of easy because we can think of 2D easily. Okay, makes sense so far? Cool, all right. I don't know if that was already known for all you guys, but that's fine if it's not, or if you guys did. All right, so then I say, okay, like when we actually try to use this, right? When we try to feed in something, so we have a picture, and this is where it's good to realize is that whenever we feed in any kind of picture, I'm gonna do a really low resolution picture of something like, I don't know, yeah, a shoe. That looks kind of like a shoe, right? Yeah. Okay. If we have something like a shoe here in this picture, this is really just a bunch of numbers. This is really a matrix of numbers. So what we can do is actually feed these numbers into a neural network as input and then build up our neural network architecture and output saying, oh, is it a shoe? Is it a shirt? Is it, a dog? Is it a picture of, my friend or whatever, right? The thing is to remember though, is that we can't just simply feed in these numbers into the neural network, right? So one thing we have to do, we have to make, because it's 2D, it's a matrix, right? Well, vectors are the only things that you can feed into a neural network. So we have to flatten out, we have to flatten our matrix to a vector. So the way this basically works is that we take each row of numbers. So if you imagine like this is the row, the first row of numbers, you take this first row, so this is row number 1, take the second row number 2, and let's say this third row, number 3, and you flatten it so that way the vector looks kind of like this. So these are all still numbers, but we have 1, 2, 3. Okay, so now we can actually feed into a neural network and actually, feed the numbers through. So you can imagine if your picture is, let's say, something really simple like a 10 by 10 pixel image, that means there'll be a total of 100 inputs, right? So that's all the inputs going through. There's an issue with this though. And you can already see me kind of talk about it here. It's the spatial information. And so what I mean by that is that if you look kind of back, I can kind of get rid of these parts. Let's make it a little easier. Is that if we split this up into, if we split this up into like, let's say this little box right here, let's say this is like the very first row and this is like the second row, okay? These points right here are close together. Those are kind of like, they should be related to each other in some way, right? However, when we put into a vector, those points are going to look like right here, and then maybe right over here. So what's going to happen is that we're losing information about how close things are. And you can think about this, it's kind of harder for the neural network to really understand where things are because essentially it's just being fed just a line of numbers. And there's no like saying, oh, well, this number and this number are supposed to be really close together. So this is where we'll actually see convolution neural works really well. But basically the main idea here is that it can do decently for small images, but when you start getting like more, think of like higher resolution, so like pictures of like people's faces or cats or, all that stuff. As we get higher resolution, there's going to be more lines of pixels, which means like this pixel that looks like right here, like let's say it's on my face, and like there's a pixel like right here by my face, they're going to be like really far away on the vector. And that's going to be hard to relate those back to each other. And not just those ones, but also everywhere. Okay. So, but just for demonstration, we can actually see how this works with multi-layer perceptrons. So I think the curriculum has something similar to this where you feed in MNIST, I never know what to pronounce it. I just like to read things. But you can see here, basically what we're going to do is we're going to load in the MNIST. However, to make things a little fun, we can load in a little different data set. So instead of like the classic like numbers, you guys know what I'm talking about with MNIST. Oops, let's go ahead and clear that part. You can see here, that's not what I meant to do. Images. So this basically is like a set of numbers. I think it's 28 by 28 pixels of written numbers. So you can kind of see the general look of these guys. So that's kind of like MNIST, but for numbers, and that's the classic one. There's another version of this, which is basically fashion, which turns out just to be pictures of little different fashion items. So you can see like a shoe, a shirt, a blouse, or I don't know what that is, a shirt. But the idea here is we have different items and stuff like this. And this is also, I think, by 28 by 28. And we can feed this in then into the neural network and see how well it does. So the first thing we have to do, though, this is where the image processing really kind of matters a whole lot, is that we have to rescale it. Because remember, these numbers are going to scale from 0, are going to be between 0 and 255. We need to scale it down so that the numbers are just between 0 and 1. Because a neural network really likes numbers between 0 and 1. It's not very good with numbers that are very big. So we're going to rescale it. So the simple way we can just do that is just divide the actual array of numbers. So note this is X train, right? We're taking these images and we're just dividing all of it by 255. And note that we also do that for the test set too. Okay. So, oops, I didn't set them. Sorry. People messaging me on Slack and I realized I didn't put them in a meeting. But okay, so once we have that, it's like, okay, cool. And then we can also one-hot encode basically what category. So there's 10 different classes. This is typical stuff, right? So this is some really basic data processing things. Okay, now we can actually build our model. So this is how the model would look like. It's like, okay, we have our data our values in our pixels now look like between 0 and 1. And then we have our categories all set for Y-train, Y-test. Let's go ahead and build our model. So right here, just built basically a sequential, what's it called, multi-layer perceptron, right? So built my neural network. And basically what I'm doing first is I'm flattening out whatever the input was. So remember, we still have a 2D set of numbers, right? So a matrix of numbers. We need to flatten this to make it into 1D. So note that I have this flatten layer, which is built into Keras right here. So I'm going to go ahead and flatten whatever the input was. In this case, the input shape is just going to be X-train slit shape. I could have said specifically like 28 by 28, but this makes it easy, right? So I can go ahead and input this guy in here, and then I'm just calling it a certain name so I can know how to reference it. And then it's like, okay, cool, I got my input in here. Let's go ahead and feed it to the next, our different layers. So you can see here I have my hidden layer. In this case, my hidden layer is going to have 75 neurons, right? Note that I have ReLU right here. I'm just naming it. Look at how I added a dropout right here. So I added a dropout layer with a 20% chance of each neuron not being used that round. And then I have my next layer, which should be the hidden layer number 2, but that's fine. Hidden layer number 2 with 75 as well, activation ReLU, dropout, so on. And then my classification layer, which is my output layer, right? And that's going to be 10 different classes with activation softmax. So remember, softmax is going to basically move those values between 0 and 1. So basically, it's the percent of like how likely it should be. Okay. So I go ahead and run this guy, and you can see my model summary right here. And you can see 65,000 parameters, right? It's not bad. So 784 by 784. I guess that's 27 by, that's 27 squared. Is that right? No, that's wrong. It's it is 28 by 28 squared. Okay. Okay. So then we can actually go ahead and compile it. So note that I'm using categorical cross entropy. Basically, that is the thing that's going to be the way I judge how wrong I am, right? So since it's category 0 through 10, and we use cross entropy, there's other things you could do too, but we're just going to use this one because it's pretty common. Note my optimizer, hey, and Adam, we just learned about that. And we have a metrics, accuracy. We're not doing anything special with this. This won't change how the model learns, just enough essentially to give us some outputs and stuff. Okay, so I go ahead and compile it. So now it's like, okay, my model is basically built, but now I need to actually train it, right? And I actually have to fit the model. So note that I basically just keep the best checkpoint here. So I'm actually going to go ahead and keep the best one. And I'm going to go ahead and train it with this data, Y-train being the results. I'm using batch size, is actually using kind of like stochastic gradient descent, where essentially I'm feeding in a batch at a time, right? And then I'm only going to run it for 8 epochs because I have a computer here. It's not going to do that great. And then you can see some callbacks is just basically for us to save the model. Validation split, because I didn't make a validation set already. I had to put it just here. And then just verbose just allows us to see the results. Note shuffle equals true. And so when I can actually get the batch size. So if I'm doing a batch size and getting certain batches, I'm shuffling it through. Okay. So we go ahead and fit this. And we can actually see this one progress forward now. So you can actually see the epoch being trained. And as you can see it being trained, you can actually see the loss hopefully going down overall, the accuracy going up. And then when this epoch finishes, you can actually see the overall loss in accuracy as well as the validation loss and the validation accuracy. So we hope the validation accuracy is actually going up as we train this thing forward. Okay, you guys all see that right now? And you can see it takes about 5 seconds per epoch in this case, because it's a relatively small data set, and there's only 48,000, and they're relatively small. They're only 28 by 28 pixels, so pretty decently going through. And you can see here, hopefully, kind of like looking a little bit on validation accuracy, you can see the accuracy hopefully going up here. So that means we're still doing pretty well. Okay, in fact, I probably could have gone even further than just this part. So I can actually evaluate it now, and so I'm going to evaluate it on X tests. Okay, and if I do this now, you can go ahead and see I have an 87% accuracy. So pretty good. Okay. Now, this data set will do fine with a machine or a basic neural network. However, as we get more and more resolution, it's just not going to do very well. Okay. All right. Any questions on like kind of what I showed a little bit? So I got to show you a little bit of like basically another implementing neural networks again, and you can see it's not too hard to actually write it out. Mostly it's just putting on these different settings and stuff. Okay. So, all right. So let's go ahead and talk about CNNs. So, like I said, like as neural networks, what's it called? As resolution gets higher and higher and higher density of pixels and stuff like this, you're going to lose information of things that are close by. So we can talk about like CNNs, convolutional neural networks, and say like, why are they better? So basically the idea here is we can use convolutional neural networks, what's it called, and look at essentially where the patterns kind of exist nearby. So kind of like I said, like seeing that associated area. So what's kind of cool is that like I said, it's usually associated with like computer vision and images, but note that like speech pattern, like for example, audio, it can also use convolutional neural nets, basically saying, like you can kind of think about like, like saying what versus where, like the sound of that air versus right? Those parts, it matters what's close by to understand from speech to text, right? You need to know not just what the data is, but kind of like what was nearby it. So convolutional neural networks can actually do really well. So you can think of convolutional neural nets do pretty well when patterns are kind of closely bundled together in some form. And this could also even be natural language processing stuff. But in general, computer vision is usually what they're associated with, because before CNNs for computer vision, like it was almost like a joke of saying like, there's no way we're going to get this in the next like 30 years. And CNNs came along and said, hey, we can actually do a pretty decent job. So that's kind of why it's associated here. I will point to a couple of things. For example, like you can see here is the text processing, like this is more NLP, and they use convolutional neural nets, basically using kind of like, what's it called? Like the sentence, and actually using convolutions to kind of see what's nearby. So it's an interesting idea. But anyway, back here. So we're going to focus mostly on like images, but just know we can generalize past that point. Okay. So this is kind of like what a convolutional neural network is. So the reason why we use this is because it basically is a neural net, like it's just our neural network, but very structured in a certain way. So we're going to find something called a convolution, and that convolution is going to be filters that essentially, in my head, are kind of like a specialized little neural network. So you can kind of imagine like, I'll see if I can draw this quickly enough and well enough, is that if you imagine, for example, let's say you have a picture and you have like a red spot, and let's just do like a blue spot and a blue spot, okay? And the idea is that we want to be able to keep this information here. What a convolution does is basically we'll take this little window and we'll actually use that window and process this into either a number or a set of numbers. So it's kind of like taking this part in there. And the way I like to think about it is like it's equivalent to saying, okay, we have this input, this red, and this red. And so what this convolution, let's just pretend this is how it works, is that it would feed out to like one red overall, so like the averages between the reds, and then just will average just on the blues based on position. And so you can kind of imagine like this would be kind of like, oh, these neurons are going to point to this new node, and these two neurons will point to this new node. Okay, and essentially that's what's going on here, but we kind of think of it kind of spatially together. So note that in a normal neural network, when we first create it, all the connections are connected, like all the neurons are connected to the next layer. Instead, we basically very specifically say, you're only going to connect in this way. And that's really what's going on here. What's cool about this then is that we can actually take this little window and we actually drag it across like our image. And I'll actually show an example of that in a second. But we'll actually drag this little convolutional filter, and we can drag it across the image. And what's nice is that we can actually take each of those like little images right here and convert it into a single number. And you'll notice here is that there's a whole bunch of like extra pages like here. You're just like, why is there like so many like, you imagine like little paper going through here, is that when we do the convolution, we drag the convolution all the way across our full image. And this will create basically different numbers kind of like as it's getting dragged across, like number here, number here, number here, go across, number here, number here, number here, number here, number here. So note that it's going to basically keep that spatial information. But we can define these weights. So remember how I kind of like said this like a neural network? This convolution kind of has like essentially the weights within there. Like what are the numbers within here? You can adjust those numbers however you want to do different things. That's what each of these guys right here are basically different adjustments to the numbers. So in this case, it looks like there's 24 or yeah, there's 24, no, I have this wrong. Oh, it doesn't say how many there are in here. It says N1. There's N1 different filters essentially. And basically there are different ways we can draw, like change the window and drag it across. And you can basically create these different set of features. And you'll notice as it kind of goes across here, this thing will get longer and longer and longer, while the size of this is going to get smaller and smaller and smaller. So what we're going to do basically is the idea of a CNN is that we're going to take spatial information and summarize it into a number, but represent that in many contexts. So we'll see in a second is that this convolution could be used just to detect edges, or just to detect, or let's say like only detect left edges and only detect right edges, or only detect blur, or only detect, what's it called? Like high contrast or something like that. Like those are the different filters right here, basically all those different things. And then we feed them forward to the next part. And we can actually take convolutions over convolutions, and we can keep going deeper and deeper and deeper in this way. And so it works very similar to a neural network, where essentially we're finding patterns within patterns within patterns. You also note that we'll talk about this next time, max pooling layer. This max pooling layer right here, this is going to basically be related to kind of like summarizing even further. So essentially we're making the data even smaller to make it easier to process it. Okay, so this is kind of like an overview of like what this convolution looks like. You can see basically we have a convolution, and then we have a pooling layer, and then we do another convolution, and then we do another pooling layer. And note that this basically each time the size of these papers are getting smaller in resolution, but they're getting longer and longer, to the point right here at this very end is that ideally we essentially have very little like pixel information. Like there's very little information about like what's actually in that picture right there, but it represents saying like, oh, this is really strongly like a bigger numbers if, there's a whisker in it, or bigger numbers if there's a wheel in it, or bigger numbers if there, is hair in it, or, something like that. And essentially these become little context clues. And so then what we can do, we can feed these context clues, basically, these features, these context features, and feed it into our normal neural network that we've learned before. Usually we call it a fully connected neural network. And essentially we feed these features then, say, oh, that has, this fuzz, like, oh, it has whiskers, and feeding it forward. And then we can build our neural network. And then at the very end, actually have our output of saying, what is that class? Is it a dog? Is it a cat? Are they numbers in this case, or whatever you're looking at? Okay. Does that make sense, everyone? More or less? I know it's a lot kind of taken. So, but the general idea here is like, think of it just like a neural network, but instead of doing like each layer being like like neurons, each layer will actually be convolutional filters, essentially. Okay, so before we kind of stop here, I want to show really quickly. Oops. I want to show you, I know this is kind of like, I'm going to skip around a little bit. This is another depiction of this filter, and you can see the same idea is that basically you can think of each of these are different layers of like different like filters, and then kind of getting stacked on top of like a stack of papers, and you'll notice that it's getting wider and wider and wider, but the resolution kind of going sideways. I don't know how this is going, but the resolution right here is getting smaller and smaller and smaller, but the amount of context is getting larger and larger and larger and larger until we finally feed this full like feature context into that neural network. But I wanted to show you guys this overall thing. Where is it though? That's not what I wanted though. Filters, here it is. No, I don't think that is it. Oh, here it is. Okay, this is what I really want to show you. But this is another depiction of like that convolution being passed through. You can imagine this red is the image. This blue is representing like different numbers. So different like shades are different numbers. And basically it gets dragged across, and whatever these numbers represent, they're summarized into one single number represented as purple. So you can kind of think of like this matrix times whatever numbers are in here, create one number right here. Okay, so I think an easier way to see this though is this great blog post. So you can see here basically on the right, or sorry, on the left is our like actual picture represented with numbers. So you can see the numbers going from like, 67. It's really small. I don't know if you guys can see that really well, but 61. And you can see on the right side where the picture actually is. And then you can see right here's the full size picture of like the real size without it being like blown up. But what's kind of cool now is you can then take it, they show this part, you can imagine this little, you see this little red square on the left. This guy right here is taking the values on the left side and comparing it into one value on the right side. Or, sorry, not compare, but creating one value on the right side. So if I drag this across, you basically will create new, new values essentially. And note that the way you find these values, if I can do this right here, you can see basically it's based on these numbers. So like whatever this number, let's say, I don't think I can do this well without dragging across, but 0 times whatever numbers in the top left, -1 times this in the part right here. And you can see all those numbers, and that will create a single number. In this case, let's say 358. So you can basically have this filter and you drag it across and you create now this kind of like overall filter, which is, or sometimes called kernel, but, or not kernel, we call this like our actual filter. And this is like one of the little pieces of paper that I showed before. But what's cool is that we can do different things. We can change what these values are. This is what's called our kernel of how we define these numbers. So for example, the blur one, you have different values right here. In this case, it looks like it's taking a fraction of whatever value is. And you can see the overall result on the right here. Same thing you can do, like, for example, like, let's say an outline. You can see here, it's only doing -1, -1, -1, except for 8 in the middle. And this creates the outline. So basically you have a stack of all these different, you know, filters made by the kernel on the same image. And that's how your overall stuff is. So it's kind of cool because you can, this one actually you can pick your own file and upload it onto here. But you can kind of see it really quickly, like what happens to the overall look. And so the idea here is that we can actually basically build up a new set of, what's it called? New set of features essentially, based on context of saying, you know, is it the outline stuff? And note that, you know, we're technically giving these numbers would be adjusted and stuff like this. You wouldn't like specifically say, oh, I'm going to use, you know, these exact values, but this gives you that idea of like how these different numbers can give you different, you know, outputs at the end. Okay. Does that make sense? Okay, cool. So, yeah, so this is actually found in there. So I'm going to stop it here. And I realized too, is that we actually won't have our next group until the new year. It gives you plenty of time to kind of catch through up and go through, you know, neural networks into convolutions. We didn't talk about all the different parts of convolution neural networks. So I guess we'll talk about that in the new year then. We'll talk about convolutions and we'll talk about transfer learning and how's that used. And then we'll go right into natural language processing. Okay. Yeah. Any overall questions on this guy? I know we're kind of over, but do you guys have any questions in general, at least the stuff that we talked about from CNNs or the idea of just feeding in images?
I've heard of some different CNNs like fast R CNN and faster R CNN. Did we cover any of that?
Yeah, we won't cover that specifically, but there's modifications you can definitely do with convolutional neural nets. And different ways you can kind of change up the kernels and stuff. There's also fully convolutional neural nets, which we don't talk about in the curriculum. So right now you can see like at the end is kind of attached on the very end is a fully connected neural network, like we've seen before. You can instead just attach another convolution at the very end here instead of a neural network. And you can actually see the activations of like where basically, and so the one problem with this thing, with this architecture, it'll just tell you there is a cat in it. It can't tell you where the cat is. It's just saying there is a cat because our spatial information is lost. However, you can create a fully convolutional neural net where what it'll do then, it will actually show you in the pictures that, oh, this is a cat. Where in this picture is it highlighted as a cat? So those are some other modifications people do. There's also things like, what's it called? Oh my gosh, I'm blanking out. Skip. Oh my gosh, I can't remember now. But basically there are parts where we could skip over. So instead of going fully connected like this, you can actually skip over the different layers and stuff like that. And that actually turns out to do a pretty decent job in conveying extra complexity and stuff like that. So there's some architectures like ResNet 50, VGG16, ImageNet. There's these different ones that use those kind of techniques and actually does a really, really good job. Can like identify over like 1,000 different classifications for whatever image. And they're like designed for like high resolution. So yeah, know that basically at this point now, like all the things that we're kind of talking about, there's like so much you can do and so many different areas of like kind of like branches off and how you can modify these things. And so it's pretty cool world we live in right now. Yeah. Cool. Yeah, so I guess I'll go ahead and stop the recording here unless you guys have any more follow-up questions. Yeah. Okay.